Recall that the Chebyshev inequality tells us that if we know the expected value of a random variable and the variance, then we can use those to say something about probabilities. That's the standard Chebyshev inequality. Chebyshev proved another inequality called the one-sided Chebyshev inequality that tells us something similar, something about probabilities, assuming we only know expected value and variance. So let's recall the other inequality first. So if we're given a random variable with some expected value, say mu, some variance, say sigma squared, and any number k greater than 0, we have that the probability that x differs from its expected value by more than k being less than or equal to sigma squared over k squared. Now this inner inequality that says, the inner inequality here in the parentheses says that x is at least mu plus k, or x is less than or equal to mu minus k. So sort of two parts here. So a natural question is, what if we just want to estimate one of these? Estimate or put a bound on. So the one-sided inequality does exactly that. So the theorem, which is the one-sided Chebyshev inequality, says with the same hypotheses, if we have some random variable x with some expected value, say mu, some variance, say sigma squared, and any number k greater than 0, then we have that the probability that x is greater than or equal to mu plus k is less than or equal to sigma squared over sigma squared plus k squared. And we also have the probability that x is less than or equal to mu minus k, so the other half is also less than or equal to sigma squared over sigma squared plus k squared. Now the proof of this in the book, I'd say, is deceptively short. Ross left out a couple of steps that I think are kind of difficult, so I'm going to put them in so that it's not so mysterious. So first of all, let's suppose we'll do the case where mu is equal to 0, so the expected value of x is equal to 0, and then we'll do general mu. So let's suppose first that mu equals 0. So we're looking at the probability that x is greater than or equal to k. I want to rewrite this as the probability that x plus b is greater than or equal to k plus b, because this is going to help in the proof. So we'll pick a number b that's greater than 0 and just write this inequality as that inequality, which is exactly the same. Now actually I want to get ready to use Markov's inequality that requires a random variable to be a non-negative random variable. So even if b is positive, that doesn't make x plus b positive either, because x could be less than negative b. So let's square this. So this probability that x plus b is greater than or equal to k plus b equals the probability that x plus b squared is greater or equal to k plus b squared. Well, almost. If I just leave it like this, I'm lying a little bit. Because if x plus b is positive, k plus b is definitely positive, because we're saying b is greater than 0 and we're assuming k is greater than 0. If x plus b is positive, then these two are exactly the same. But if x is a negative number, which is really negative, let's say k and b are like 3 and 5 and x is negative 100, negative 100 plus 3 is negative 97. Squared is going to be a lot more than 3 plus 5 squared. So we have to subtract the probability that x plus b, so that x is negative, and x plus b in absolute values is greater than k plus b. This is one thing that was left out of the proof, kind of. And actually, it's not crucial to get this expression exactly right, because all I want to conclude from this sentence is that the probability of x plus b being greater than or equal to k plus b is less than or equal to this probability with squares. And this probability with squares is something we can apply Markov's inequality to. So we're starting with probability that x is greater than or equal to k is equal to this. And that is less than or equal to the probability that x plus b squared is greater than or equal to k plus b squared. And by Markov's inequality, this is less than or equal to the absolute value, this is the expected value of x plus b squared. I mean that square to be inside here, over k plus b squared, because this is a non-negative random variable here, x plus b squared, and the probability that our non-negative random variable is greater than or equal to this number is the expected value of our non-negative random variable divided by this number. All right, so let's simplify this. Now the expected value of x plus b squared over k plus b squared is, well, let's multiply this out. Expected value of x squared, this is a capital X, plus 2bx plus b squared all over k plus b squared. And then expected value is linear, so we can write this as expected value of x squared plus 2b expected value of x plus expected value of a constant is just a constant. All of that over k plus b squared. But this simplifies further because we're assuming first that the expected value of x, mu, is 0. So 2b mu is just going to be 0. Expected value of x squared is not necessarily 0. So we'll keep the expected value of x squared and b squared and get rid of that. So expected value of x squared plus b squared over k plus b, the quantity squared. All right, probability that x is greater than or equal to k is less than or equal to this. I'll write that. So the probability x is less than or equal to k is less than or equal to expected value of x squared plus b squared over k plus b squared. Oh, actually, before I'm running out of space. That's okay. I'll just write this again when we need it. All right, now the end of the theorem says we need a sigma squared in here somewhere. That's the variance of x. Now, we actually have it already. Recall that the variance of x is expected value of x squared minus expected value of x, the quantity squared. And if expected value of x is 0, this is just expected value of x squared, which is not necessarily 0. So there's variance of x right here. So the probability that x is less than or equal to k equals variance of x plus b squared over k plus b, the quantity squared. Sigma squared plus b squared over k plus b, the quantity squared. Now this is supposed to hold for all positive numbers b. For all b greater than 0. Now if we choose a value of b strategically, we're going to get the inequality we want. So in particular, if we let b equal the positive number sigma squared over k, k is positive, sigma squared is definitely positive. Then this fraction is so we've got sigma squared plus, if b is sigma squared over k, then b squared is sigma to the 4th over k squared. Let me make the sigma squared a k squared, k squared sigma squared over k squared. And then what do we have on the bottom? K plus b is sigma squared over k. All of that squared. Why don't I make this k a k squared over k to help with the fractions? K squared over k. Alright, so we've got something over k squared in the denominator and something over k squared in the numerator. So this simplifies to k squared sigma squared plus sigma to the 4th over k squared plus sigma squared, the quantity squared, over the k squared. That's going to cancel with that k squared. And let's see, if we factor a sigma squared out of the top, that's sigma squared times k squared plus sigma squared over k squared plus sigma squared, the quantity squared. So these will cancel, leaving just one of these on the bottom, which is sigma squared over k squared plus sigma squared. All right, so we proved that this should be less than or equal to. The probability that x is less than or equal to k equals this expression. All right, so let me write this down. So the probability x is less than or equal to k is less than or equal to sigma squared over sigma squared plus k squared if the expected value of x is 0. So we just finished the first case of the proof. Now we want to look at general x that has expected value of mu, which might be different than 0. But this second case is much shorter than the first case. We've almost got it. And so now suppose expected value of x is mu. Not necessarily 0. And let's define a new random variable y to be x minus mu. Then the expected value of y is expected value of x minus mu, which is mu minus mu, which is 0. And the variance of y is variance of x minus variance of a constant is 0, so this is just variance of x, sigma squared. All right, so y is a random variable that has expected value of 0, so we can apply the inequality we've got down here. So that means if we want the probability that x minus mu is greater than or equal to k, actually let me say, the way we stated it was the probability that x is greater than or equal to mu plus k, and that's the same as the probability that x minus mu is greater than or equal to k. This is the probability that y is greater than or equal to k, because y is x minus mu. And this is less than or equal to the variance of y, which is sigma squared over sigma squared plus k squared. By the first case of the proof. All right, so that actually was pretty short, going from expected value equal to 0 to general expected value. All right, now I had two inequalities up here. There's x more than k greater than mu and less than k less than mu we want also. So the probability that x is less than or equal to mu minus k equals the probability that, I could write this as mu minus x is greater than or equal to positive k. Mu minus x is greater than or equal to positive k. Now mu minus x is negative y. The probability that negative y is greater than or equal to k. Now the expected value of negative y is just negative expected value of y. So since the expected value of negative y equals negative expected value of y, which is negative 0, which is 0, and the variance of negative y equals variance of a constant times a random variable, is we can pull the constant out and square it. So that's negative 1 squared variance of y, which is just variance of y, which is sigma squared. We have the probability that negative y is greater than k is less than or equal to also sigma squared over sigma squared plus k squared, exactly the same fraction. write that again, and we'll do an example. Mm-hmm. All right, let's write the result down again and then do an example. So we're given a random variable with expected value of x equals mu, variance of x equals sigma squared, and any number k greater than 0, the probability that x is greater than or equal to mu plus k is less than or equal to sigma squared over sigma squared plus k squared. Also, the probability that x is less than or equal to mu minus k is the same thing, or less than or equal to the same thing. Sigma squared over sigma squared plus k squared. All right, let's go back to the example that we looked at when we first did Markov's inequality. Suppose the expected value of x is 6 and the variance of x is 4. The question is, what can we say about the probability that x is greater than or equal to 9? So Markov's inequality says that the probability x is greater than or equal to 9 is less than or equal to the expected value of x over 9, which is 6 over 9, which is 2/3. Now, Chebyshev's inequality, the primary inequality that we learned, doesn't say. Because it gives us the probability that the difference between x and 6 is, say, greater than or equal to 3. It gives us an expression for that, but the difference between x and 6 being greater than or equal to 3 means possibly two things. This could mean that x is greater than or equal to 9, or x is less than or equal to 3. And we only want the x greater than or equal to 9 part. So the Chebyshev's one-sided inequality says that the probability that x is at least 3 bigger than 6, maybe I'll write this, the probability that x is at least 9, the probability that the difference between x is at least, between x and 6 is at least 3, and x is bigger, is less than or equal to variance, which is 4, over 4 plus the square of this number here, 3 squared, which is 4 over 4 plus 9 is 13. 4 over 13 is a lot less than 2/3. So Chebyshev's one-sided inequality gives us a stronger bound than Markov's inequality gives. So since 4/13 is less than 2/3, Chebyshev's one-sided inequality gives a better bound than Markov's inequality. And that shouldn't be too surprising, because Markov's inequality gives us information if we only know expected value of x. If we know expected value of x and variance as well, that's more information. So that more information should lead us to more accuracy in the end. The end.